It says, as usual, Zoom has his own life. It's nice to give a talk at New York Group Series Seminar. And I will talk today about several things which were sort of started here in New York. So it's exponentiation in groups. Using, that's how Gilbert usually gave talks when he was talking about general things. So I decided to give a talk like, not like Gilbert, it's impossible, but about some view what's going on with exponential groups right now. And it was 2 days ago was Miasnikov's 85th birthday, so on September 26th. So I thought it's a good idea to do it now. How to all right. That's the outline. I will talk about this exponential group, about variations on non-commutative modules. Then we'll define the main operation, its tensor completion. And then we'll do some examples, Magnus completions or Linden's completion, then Hall's completion. And the idea is to see whether this tensor completion, how it relates to all these known completions. Is it natural or not? Let's start with the abelian groups where real modules came from. So from abelian groups to vectors in vector spaces, the big step was to introduce modules over rings. And the crucial technique was the tensor completion. So it's not just increasing, extending scalars, but it's a very nice operation which has a lot of good properties. And the main thing is how to extend this theory to non-commutative groups. Okay. In all attempts, people try to mimic the natural Z exponentiation on a group. When you take element G in G and map it to G to the n, which is a product of G n times. So it's a reasonable kind of approximation of a Z module. And really all attempts are kind of trying to do something similar, but putting extra axioms. And what are axioms people put in depends on the structure or algebraic nature of the group G. So this is the standard definition of R group. So let R be an associative unitary ring, arbitrary, maybe non-commutative. A group G is called an R group or group with R exponentiation if it comes equipped with an R action, which I will write also as exponentiation, like that. G goes to G to the alpha. Alpha is the element from the ring, satisfying the following axioms. So it's first type of axioms are kind of what we expect. This axiom says that it's an action, and this is how we would like to have how some of the scalars act. We wanted to commute with conjugation because the standard Z exponentiation has this property, and this is really crucial. I think it's important axiom. And Roger Linden, long time ago, stopped at that first three, and he considered this as R group. When we started working on exponential groups with Remesnikov, we realized that one more axiom is missing, this one. Now people refer to it as MR axiom. But what does it say? It says that if two elements G and H commute, then exponentiation is like in module action. In other words, on abelian R subgroups must be just modules, R modules, which is convenient because you don't want to have abelian R groups to be far from R modules. I have to say that all examples that Linden considered without introducing this axiom, but these examples always satisfied these axioms anyway. Just, I will say a few words later. So these are four axioms which define R exponentiation. And the action of R is faithful if G alpha is not equal to non-zero alpha should act non-trivial on some element in G. In this case, if it's faithful, I will call it a ring of scalars. Again, it could be that R is non-commutative. All right, so what are examples? There are a lot of examples. Some of them I just mentioned here. Every group G is Z group because if you try to mimic the exponentiation, really. Every group of period n is Z mod NZ group. R modules of a ring are just abelian R groups, the same. Divisible groups are, in fact, Q groups. Unipotent groups, G over a field K, say, or binomial domain, are K groups. Propy groups are ZP groups, where ZP is a ring of p-adic integers. Profinite groups are Z hat groups, where Z is a profinite completion of Z. So there are a lot of groups which become sort of R groups for suitable ring R. Where we can find these rings of scalars in groups, really? Where to look for rings of scalars? And the idea comes from ring theory, where you can define what is a centroid of a ring, which plays the role of maximal ring of scalar in a ring and makes this ring into an algebra over this centroid. So if you think a little bit how you can do it for groups, you can come with the following definition. So if you have a mapping phi from G to G, it's called normal. Phi is normal if it commutes with conjugation. It's a map. It's not a homomorphism, but it's normal. Normal homomorphisms are precisely like that. And the second definition, quasi-endomorphism. Phi is quasi-endomorphism if it acts like endomorphism on commuting elements. In other words, if X and Y commute, phi acts on the product XY like an endomorphism. So it turns out if you consider gamma of G, the set of all normal quasi-endomorphisms of G, it is an associative ring with identity. This is the centroid of G. It's not difficult to prove. It's actually quite easy. But important property is that for any group G, the centroid is a ring of scalars for G. In other words, G is gamma G group. G, action of gamma of G on G satisfies all axioms of the exponentiation, all 4 axioms. Moreover, gamma of G is the largest ring of scalars of G. In other words, any other ring of scalars naturally embeds into gamma of G. So if you have a ring of scalars, every element acts on G, so it gives a map. And this map will be normal and quasi-endomorphism. So gamma of G is the largest ring of scalars. Of course, it's faithful. And we know where we can look for maximal rings of scalars. Centroids were computed for some groups. For example, free groups, torsion free, and so on. In general, for CSA groups, CSA group is CSA if every maximal abelian subgroup is malnormal. It's difficult to believe, but it's quite large centroids these groups have. As well as for some nilpotent groups, like free nilpotent groups and unitriangular over Z, some others. Centroids in these groups are actually very small. It's basically Z plus some nilpotent ideal. The ring is very simple. It's kind of Z plus a nilpotent ideal. It's very interesting sort of to understand some open questions that I would like to discuss today. It's a lot of them related to centroids. For example, how to compute these centroids. For example, if you have nilpotent groups, you can go to corresponding Lie rings and compute centroids there. For free or hyperbolic groups, it's a different story because they're CSA. So you can, on the class of conjugated centralizers, you can independently define the action and then expand it to the whole group. Since abelian subgroups are malnormal, you can do it. It's well defined.
Okay, sorry. So can you tell us what the centroid of a free group looks like? You know, I mean, you told us that it's been computed, but what is it?
Yeah, it's Cartesian product of rings Z, countable Cartesian product. So it's a huge. So basically, for every class of conjugated maximal abelian subgroups, which are centralizers, of course, in a free group, you have an action by Z on the centralizer, natural action, and you expand it everywhere. There is a big difference. I didn't want to say it because it's faithful, but it's not. It will be gamma G torsion there. So if you go not only to rings of scalars, but those rings of scalars for which the group does not have a ring R torsion, then in the free group the centroid becomes just Z, which you want. I will say a few words later, so you can. It's a big ring, but you can find more natural subrings in such centroids. in each case. All right. So in the main operation, tensor completions in non-commutative case. So this is the only kind of long definition, but it's standard. So what did I do here? I take the notion of tensor completion in theory of R modules and mimic it to the non-commutative case, or more generally, the same notion of tensor completion in categories. So let's see. You have a group G, arbitrary group, no restriction. R is arbitrary unitary associative ring. An R group denoted G tensor R is called a tensor completion of G. Actually, I didn't write, but tensor completion of G. If there is a homomorphism from G into its tensor completion, which satisfies two conditions. First of all, the image of G, lambda G, generates tensor completion as R subgroup. As usual, you can define R homomorphism, R subgroups, and so on. R subgroups, for example, it's a subgroup which is invariant under R action. So lambda G, R generates the whole tensor completion, and tensor completion satisfies the natural universal property. Means if you have homomorphisms from G into R group H, you can make the diagram commutative. So you go from G by lambda to the tensor product, and from tensor product back to H, and the diagram is commutative. So for every homomorphism phi, you can get it through tensor completion. So word by word is a classical definition from category of modules. Sometimes this group is denoted by G to the R. It's that what Linden, Baumschlag, and also with Remesnikov, we did it sometimes because it's just shorter. Okay, there is the operation tensor completion. From general nonsense, it means from universal algebra, you can immediately deduce some properties. For every group and every ring, there exists an R completion, tensor R completion. The completion is unique up to an R isomorphism. Moreover, if you start with a free group in the category of all groups, then F to the R, its tensor completion, R completion, is a free R group in the category of R groups now. In this case, the canonical homomorphism lambda that I was showing in the definition is injective. So this completion is faithful in this sense as well. It's not true that arbitrary R completion is faithful. It means G embeds into G to the R, to the R. It's not true. Sometimes it embeds, sometimes it does not. But for free groups, it does. So in the next several slides, I will show that completions, tensor completions, they have very nice algebraic structure. For a wide class of groups, not always, but always I don't know, but for a wide class of groups, like free groups. So just to remind you the definition, subgroup H of G is called conjugately separated all normal if for any X in G which is not in H, intersection of H and conjugate of H by X intersect trivially. So CSA originally meant conjugately separated maximal abelian subgroups. CSA, abelian. At that time, I didn't know what that there is a corresponding notion of malnormal. So a group is called CSA if it's all maximal abelian subgroups are malnormal. Free, torsion-free, hyperbolic, and many other groups are like that. So what do you do? How you construct tensor completions? It's very simple operation. Extension of a centralizer. If you have a group and M is a maximal abelian subgroup of G, then this amalgamated product, what do you do? You take G, free product with M tensor R. M tensor R, it's a tensor product in the category of modules, abelian modules, as usual. And then you amalgamate M in G and M in this tensor product. Again, you need to be able to amalgamate. Sometimes you just, maybe it's not embeddable into tensor completion, M tensor R. But in my case, all groups will be like here. Torsion-free groups, it means M is torsion-free and R is characteristic zero ring. So this tensor completion is always faithful. M embeds. In this case, you amalgamate. So it's a free product with amalgamation. Very nice, because one of the subgroups is just abelian, this one. Okay. And it turns out you need to prove, but it's not very difficult, but technical, that if you start with a torsion-free CSA group and R a ring of characteristic zero, then tensor completion, which exists from general nonsense, in fact is a union of a chain of extension of centralizers. You just extend all centralizers, and when you do free product with amalgamation, new centralizers which are cyclic appear. So you extend again and keep going. So there is a it depends on the group. If group G is countable, then in countable chain, it's a countable, it's a direct limit of countable chain. The canonical homomorphism is injective, so that's crucial. Tensor completion is faithful. And the resulting group is also torsion-free and CSA, which is also, you will see it's important. When I say why, I say it has a nice algebraic structure, because every member of this chain is just a sequence of extensions of centralizers, iterated extensions of centralizers, sort of obtained by very nice amalgamated products, free products. So using Bas-Serre theory, you can do a lot of things. You can study various algebraic, geometric, algorithmic questions about the completion. So it's really nice. Bas-Serre theory is designed for this, really. Oops. You can improve on this construction, and we did with Olga Harlampovich and Rizas Klinas. In fact, you can organize this direct limit such that will be a Fraisse limit of iterated extensions centralized. And Fraisse limits, they are very particular type of direct limits, so it has very universal and homogeneous properties. So it was done for a ring of polynomials in one variable with integer coefficients. for arbitrary torsion-free hyperbolic group. In fact, if you think a little bit and adjust the construction, you can do it for arbitrary ring R of characteristic 0. So R completion of torsion-free CSA group G to the R is again a Fresnel limit. So it has very nice algebraic properties, but also some universal property common to Fresnel limits. I have to say that in this case, if R is arbitrary, for example, it could be not countable, the standard Fresnel class does not work because it's stated for finitely generated, say, structures or groups, for example. But here it could be. But you can adjust the standard notion of Fresnel limits. So what did we do? We define a notion of R group. We constructed tensor R completion. So we have the two main tools which we would like, we wanted from the category of modules to transfer to non-commutative groups. Now the question is, okay, we developed the theory, so why is good? Why it is good? So what can we do with this? So I would like to consider how it actually turns out that these completions appear naturally in groups. It's not quite clear now, and I would like to discuss their algebraic and algorithmic properties. And which is also very important, I think, it's to compare tensor completion with all sorts of other completions which already exist in groups, in group theory. So that's the goal for the rest of the talk. So divisible groups. Of course, probably everybody here knows what is a divisible group. It means for every element in the group, this equation has a unique solution in G. You can extract roots uniquely. Since you can extract roots, you can define the action by fractions, rational numbers. And that was done long time ago. And for every group G, the tensor co-completion that we defined gives precisely the canonical, sometimes it's called divisible hull of G, which is uniquely defined by G up to Q is isomorphism, and it was known for some groups for a long time. So it's natural because it was studied, it appeared here for a long time ago. Nothing new here. And then you can consider, as I said, a free Q group, F to the Q. So you start with a free group with basis X, you do tensor Q completion, you've got free Q group with basis X. Free object in the category of divisible groups. And Gilbert Baumschlag was the first who described, or actually, who described the structure of this group as, and he described it quite similar to what I was showing a few slides ago, is a sequence, countable sequence. It depends what the basis X is, but it's a, you get FQ as a result, as a direct limit of free root extensions. So it's the same thing, really. It's amalgamated product again. You can think about it like that. You take element G, and you want to have it not a proper power, and take cyclic group generated by X and do this amalgamated free product. So when the centralizer of G becomes Q if you add all the roots to G. And this group sometimes is called now Baumschlag's 3Q group because Gilbert was introducing and studying this construction. And with Olga, when we described when free products with amalgamation, when these products preserves hyperbolicity, we show that f to the q is a direct limit of countable chain of hyperbolic groups, of course. And using Van Kampen diagrams, we were able to prove that the Fantin problem is decidable. In other words, there is an algorithm which says for a given system of equations in F, whether in FQ, whether or not it has a solution in FQ, and if it has, it finds a solution. Basically, what we did, we proved that if there is a solution, there is a solution of bounded kind of length. You can bound it number of extensions of roots. So it's very nice algorithmic properties. It means a lot of other algorithmic problems are decidable here. Before that, of course, much before, Magnus introduced his representation of free groups. So I will describe it in a little bit more general context, but suppose R is a binomial domain. It means if you pick an arbitrary element in R, then binomial coefficient, this binomial coefficient, it is again an element in R. To compute this binomial coefficient, you need to divide by some say n factorial or something like that. So in other words, you need that the elements in the ring are divisible by some natural numbers. You can embed arbitrary integral domain into binomial domain, just inverting, say, all elements in Z. You don't need all of them, but anyway, yeah, it's the same thing, really. So starting with a set X of variable, you can form the formal power series with coefficients in R. And then if you denote by delta R the ideal generated by X in power series, then 1 plus delta R is a group of units. Every element is invertible. And because it's power series, it's very easy to invert. More interestingly, that you can define an R action on this group using just binomial series. So you expand as a binomial series. So 1 plus f alpha, 1 plus f to the alpha, f is from delta R. You can define it like that. And this series exists because it's power series and the ring is binomial. So this turns 1 plus delta R into an R group. What Magnus showed that the map xi to the 1 plus xi gives an embedding of a free group with basis X into this ring of power series. So it's injective. This map can be extended injectively as a homomorphism from free group F with basis X into the group of units 1 plus delta R. But it also can be extended uniquely to an R homomorphism from the free group R group. Indeed, because that's a universal property of free R groups. You map F into this R group, so you should be able to expand it to R homomorphism of to the free R group, F to the R. So yes, and it's called now Magnus representation. Magnus did not do it like that, but he did it for Q, say. He did it for Z, but it's he considered it for Q as well, and for some other rings. But so long-standing problem is this map when R is Q injective. And I remember that with Gilbert was obsessed with this problem as well as Remesnikov. Every time Remesnikov came to New York to work, say, on one relator groups or something else, the first 2 weeks we spent trying to prove this, that it's indeed injective. We didn't succeed, but Aiken Zapirine 2 years ago, he indeed proved that the Magnus representation, lambda R, of free group F to the R is injective for any binomial domain R. So it's not only for Q, but it's for arbitrary binomial domain. So it's maximal strength result. In particular, this group is residually torsion-free nilpotent. It's actually is residually R torsion-free nilpotent, but it doesn't matter right now. So, in other words, you can take, you can get R completion of free group inside the power series as Magnus did. So, in some sense, Magnus completion, R completion of F, is the same as a free tensor completion. So it shows that free tensor completion, indeed, in this case, it is very natural, because people thought that it's the freest completion, and indeed it is, because it's precisely the same as tensor completion. F to the R, it's embeds there. You can try to do it for arbitrary group, not CSA groups, not only free group. So if you take a torsion-free CSA group G, you can mimic Magnus representation where instead of power series, you take group algebra of G with coefficients in R. You take the augmentation ideal delta and make completion of RG with respect to delta adic topology. So it will be, I denoted by star, maybe Alina will complain, it's not C star algebras anyway. So it's a completed group algebra. So it's like infinite series, but it's element infinite kind of sums of elements, linear combinations from G. And delta R bar is the corresponding augmentation ideal in the completion. Again, you can repeat the argument. It takes much more to show that everything is well defined, but it is. So there is a similar representation. It's not known whether it's faithful or not. So the question is, compute the kernel of this map for binomial domains R and torsion-free CSA groups. So it's like K2 functor. In K theory, you would like to measure whether the freest, in this case, exponentiation and Magnus exponentiation, sort of Magnus, he didn't define it himself like that, didn't call it, but it's from his construction. So how different they are, and the kernel will measure the difference. In particular, if you take G a limit group, what is
the connection with the K theory?
Yeah, it's a connection. You will see a little bit later, but right now is just in. It looks. You have, say, think about SLN, bounded sort of, not stable case, but bounded, SLN over R, and Steinberg group of size n over R. There is a, from Steinberg group to SLN, there is a natural homomorphism, and the kernel, which is K2, in this for non-stable case, it's what measures how freest SLN, which is Steinberg group, differs from real SLN. The same thing here. So it's on intuitive level how it relates to K-theory. There is actually actual relation, but I don't have time to talk about it. Right now, it's just, it looks like similar intuition. So Heiken-Zapirain again prove that indeed, if you take limit group, then its Q completion is embeddable. So the standard homomorphism is an embedding. So again, if you start with a limit group, its Q completion is readily torsion-free nilpotent. And it's a direct limit of very nice extensions of centralizers or free root extensions. It would be interesting.
Alexei, did he did he say it in the paper or it
Yes.
easily follow?
No, he says,
He says, oh, okay.
Mhm. He actually considered R completion on F precisely. And but he expanded from free group to limit groups as well over Q. Not so. What's the big difference? The big difference here is that for free groups, it's arbitrary binomial domain. For limit groups, it's just for Q. That's what he mentioned. But I think it will be true for example, for arbitrary field of characteristics 0, at least countable. And it means since binomial domains can be embedded into fields of fractions, they are fields of fractions. So I think this question, it makes sense for arbitrary binomial rings. It might be it's faithful. Magnus' representation is faithful as well.
One quick question. I noticed that you are discussing like the decidability of the Diophantine problems for these particular structures. Now, when people have results like this, do they actually construct the algorithms to decide, or do they just show that it is decidable?
No, it's in principle you can show that it's decidable, but what I mean decision algorithm, if there is a solution, it finds one.
Okay. All right.
So
but not necessarily efficiently or anything of that nature.
No,
probably very difficult.
That's a different question, yes. Whether it's efficient or not, it's yeah, it's a separate question. I think for these groups, there is, because the equations, the Diophantine problem is decidable in limit groups. So that's what we proved with Olga some time ago for Tarski. So I think it could be expanded to G to the Q as well.
But it is probably like if you add roots, you have total relatively hyperbolic groups, right? Like if you add a root to a total relatively hyperbolic group, you probably
it's not hyperbolic because it's not hyperbolic limit groups, right?
No,
toral, yes. Toral. Probably it's a sequence of toral.
Relatively hyperbolic.
It's a sequence of toral relatively hyperbolics, but you need to have still more, right? Because there is no approximation.
You need to bound the length of the sequence.
Yeah, that's what you need to bound. Because there is no discrimination homomorphisms from G to the Q. I don't know.
No.
It's so I think it's true, and precisely along the lines Ola, you're saying, but one needs to to check that you can bound the
Check the
length.
details, yes.
Yeah.
Mhm.
Now let's go to the property completions. So you have a group G, denoted by G hat P, the property completion of G, which is inverse limit of all finite P quotients of G. As we mentioned at the beginning, every property group is ZP group. So in fact, property completion is a nice completion actually of G with respect to this topology. And the question is how it relates to ZP tensor completions. Of course, for arbitrary group G is difficult to say, but what is known, it's for free group with basis X. If you start with a free group with basis X, then its property completion is actually a free property group with basis X. So it's a free object with basis X in the category of property groups. It was known from Lazar, I think, that you can construct it this free property group inside the power series. It should be with respect to topology, but there is a similar representation, similar to Magnus. Now, the free tensor completion fx to zp is a free zp group. It's not a free property group. It's free zp group. So it's a free objects in the category of ZP groups. F of X embeds into property completion because the free group is residually P. So we know that F of X without ZP embeds into here. Property completion is ZP group, so there is an extension of ZP homomorphism identical on X from this group to its property completion. What Heiken Zepperein again proved in his paper, and he mentioned it's one of the kind of big results there, that in fact this embedding, this homomorphism is injective. So inside of free property group, there is this nice construction f of X ZP sits inside. Again, this is the construction is a direct limit of free products with amalgamations, extension of centralizers, and these free products with amalgamation is not in the category of property groups. They are abstract in the category of all groups. You can, that's the same group that I discussed before. So it sits inside. It's not that obvious, and it's completely non-trivial to prove. But we have a group, subgroup of free property group, which we know a lot of things about. Of course, it would be nice to apply free products with amalgamation in the category of property groups and get the whole thing again. Right now, this is a proper subgroup as it is. Formally, nobody proved it, but it's sort of clear that it's not the whole free property group. Okay, so it's a residually torsion-free nilpotent. And again, tensor completion by ZP appears naturally. It's not just strange universal algebra invention. No, it sits inside their free property group. You can try to generalize from free group to limit groups or some other nice CSA groups. I think it's also, it might work, but you need, yeah, anyway. So this is an open problem. Now, this is a very interesting problem. You have G, say free group or limit group, say free group, and take tensor ZP completion. Consider equations, but not where coefficients are from G. Otherwise, you will have, if arbitrary elements from this completion, there are uncountably many, you can't show it to a computer. So coefficients are in G, very tame. Is there an algorithm which decides whether a given system of equations, finite system of equations like that, decidable, has a solution or not? And if it has, finds a solution. I think it's doable, and it's quite interesting. And especially it's interesting because it relates to another very interesting old problem, for which not much is known, even though I know people, it's known very well for a long time, but not much is known really. So take a limit group G and take its proper completion. And is the Diophantine problem in this group, which is uncountable, but you can see the equations only with coefficient in the initial group G, so countably many. Is this Diophantine problem decidable or not? So the main, of course, question is for proper completion of a free group. Limit groups are similar, but it's much more complicated, and it's not clear for free group actually. That would be very interesting to see what's going on. And that's very old. How old? It's from 1970s. There is a famous, not famous, but problem which attributed to Remesnikov properly. Indeed, he put it. And it's the following. You have a free non-abelian group F of finite rank and G a finitely generated residually finite group. Is it true that if they pro-finite, not pro-p, pro-finite completions are isomorphic, then the groups are isomorphic? There are a lot of, during the last 2 decades, there are a lot of results which for various groups, but for free groups, the original open problem is still open and not quite clear what to do with this. You can try something which is easier, I believe. And these are rigidity problems for exponentiation. So you have 2 commutative unitary rings of characteristic 0. Maybe fields if you want. Suppose tensor completions of F by these rings are isomorphic. Does it imply that rings are isomorphic? So it's rigidity of ring rigidity of tensor completion. Since these groups sit inside pro-finite completion of phi group, it's reasonable to start with this. And since you can compute centroids, there is a reasonable approach to this problem because you're looking for rings inside the centroids. And these rings are, anyway, okay. And these rings are not only faithful rings of scalars, but there is no R torsion or S torsion. Second problem is dual. Let F be a free group and G a torsion-free CSA. and are an integral domain. So suppose you are tensor completion of F and G are isomorphic. Does it mean that the groups are isomorphic? Again, it's simpler version. I don't know whether it's simpler than Miasnikov's problem, but if you take profinite completion of Z, this group sits inside profinite completions of F and G. So you can try this first and then go to Miasnikov's problem maybe. Oh. It seems like I'm behind the scale, my time, right?
Yes. Maybe you should come back for another talk, part 2.
I'm sorry. It's so nice to talk sitting in home.
Because on the count of your slides, you're slightly less than halfway through, right?
So
We
what I
can
wanted.
we can have another Zoom talk next Friday. I don't know. Like it's
All right.
Yeah,
Ilya.
because we don't have a seminar next
Let's have a
Friday,
seminar
right?
next Friday. Why don't have a Zoom seminar?
For me, it's fine if you want to listen, but I want you to talk about kind of how this tensor completion in varieties like soluble groups, in particular metabelian groups and nilpotent groups, how they relate. In nilpotent groups, there is a Philip Hall completion, so-called famous, which is also Maltsev completion. Maltsev did it for Q, Philip Hall in general sort of axioms for completions. How far tensor completion of nilpotent groups from Philip Hall, and there are surprising results here. I don't want to say because I don't have time.
I suggest, Ilya, we'll have a Zoom talk next time.
I mean, that's fine by me. I'll be away next week, so somebody else will have to, you know.
I can.
So, Olga, you can be in charge of this,
Okay.
but that's fine by me. Yes. You know, so,
So,
Alexei,
sorry about this. Yes, I'm sorry.
That is perfectly fine. So we can stop here for today, you know, and continue next week.
Okay.
We can even have it in person, actually.
So we'll figure out what the plan is.
Figure this out, yes.
For continuation.
So floods are not only in nature in New York, but also in the talks.
Right. All right. Okay. Let us thank Alexei for at least the first part of the talk. Thank you.
You.
Okay. All right. So any questions about what we heard here today? So now you can unmute yourselves and ask Alexei some questions.
So you can unmute, and I should mute myself, right?
No.
It's stupid jokes. Okay.
Just a quick question. So you're probably going to talk about metabelian Q groups next time, right? Or maybe not.
More than that. No, I would like to talk about exponentiation metabelian groups, which are by actually different rings. And that's what the recent results with Olga, which are coming very naturally in first order classification. But yes, in particular, Q groups, it's just to see what the initial example is. For Q completions of metabelian groups, there are results.
Okay.
Yeah, that's what you will know.
And bounce lags construction does not carry. I mean, is it different from the one you mentioned at the beginning?
Right, it is different. You can try to adjusted using free products with amalgamation in the variety of meta-abelian groups. That would be one way. But what I will be talking, it's a different exponentiation because it's kind of more precise exponentiation, more related to the structure of a given meta-abelian group. That's what I want to show.
Oh, okay, great.
I have a question, Alexei. Do you have any ideas? Like, for example, suppose you want to make an tensor completion of a right angle arching group, which is not CSA. What could be like? I mean, when these extensions of centralizers don't work.
It's a good
What
question.
would be?
Yeah, it's a good question. It's more complicated. It should be something with respect to the lattice of centralizers. It's quite complicated there. It's
Yes.
depends on the graph, of course. So
Alexei, could you not do it by power series because you have the same kind of Magnus embedding for right-angled arc groups?
precisely.
But not in the group ring. You can just take the right-angled arc monoid and take its power series ring, and that's faithful for the right-angled arc groups. So maybe you can just, for binomial domain, do the same thing there.
Yes, Ben, you're right. That's what I wanted to say. So you can do this thing, and it's known. That's how you show that it's. So that's a way to embed, for example, in matrices. But I'm not sure that it will be a free tensor extension with this universal property, and would be nice to see. So maybe the kernel there is non-trivial, but yes, it's very interesting, very interesting question because Magnus representation is there. So
Glenn, can you repeat what you said, because it was quite I didn't understand.
You have the same Magnus representation. You can take the right-angled arc monoid, and and you can build the power series ring in the same way, and you can send the generator X to 1 plus X, and that's known to be faithful on the right-angled arc group. That's the standard proof that it's torsion-free nilpotent. And now you can do the exponentiation if it's a binomial ring in the same way. And then the question is whether Jaikin theorem still works or not. Of course, it might not. It's not CSA, but at least that gives you a concrete, candidate for what it might look like. It might not work. I don't know.
Yeah, that's a very good idea, I think.
That was going to be my question, but Olga beat me.
Yeah.
Sorry.
Alexei, I actually had a question about something that you said in the beginning and then followed up. So you had this centroid construction, and you said that this is the largest R for which G is an R group, right? But then you said that for the free group it's been computed, but then you also said that for the free group, there are it embeds into an R completion for more or less any R, right? Or whatever, right? So I mean, these two things somehow don't quite compute in my mind, right? So if there is a centroid for the free group, then it means that any R for which the R completion exists must be inside the centroid.
Yeah, it's a good question. Let me explain, because it's slightly yeah, there are two things here. Where is it? Over here. Yeah. So you started with a group G, right? And centroid is a maximal ring of scalars. Any other ring embeds there. But when you take R completion of G, it will be different centroid because the group is different. G to the R, it will be. So it will be different centroids and so on. But I suspect that centroid of this group, gamma of G, is centroid of the group G to the R completion. They're very much related. And in many cases, at least. For example, in free group, it's they are related. Instead of endomorphisms of integers, you will have endomorphisms of the ring R. But otherwise, it's the same structure as a ring. So, indeed, in gamma of G, all subrings of gamma of G are rings of scalars of G, but arbitrary ring R maybe not does not embed, because you need to take G to the R first extension, then it will be gamma of G to the R, which is a new centroid. I don't know, Ilya, does it make sense?
Yeah, I think it does. Yes, thank
Okay.
you. Yeah.
There is a more specific subring, as I said, not only faithful, but which doesn't have torsion. Ring of scalars R without R torsion. R torsion, like G to the R, is never equal to 1 if G is not 1 and R is not 0. That's no R torsion. So this is very interesting subring, and it's for free group it's Z. For other groups it's more. Anyway, I don't want to get into it, but there are very interesting subrings here.
Okay. All right. Any other questions to Alexei? Okay, if not, let us thank Alexei again. Thank you.
Thank you very much.
All right, so I'll stop the recording.